Hello, welcome back. Let's review what we have done last time. So in the last video, we just made a substitution for this Vy term. Why do we want to substitute out this Vy? Because honestly, we don't know what it is. So to kind of help us, we kind of integrate this continuity equation across y as such. So when we integrate across y, we actually get this result as a result of using Leibniz rule. Okay, so once we have Leibniz rule, we find that okay, Vy equals to V, the y velocity evaluated at 0. Then you have this integral term here plus u evaluated at x, and of course y, and d big Y dx. This big Y is going to be our boundary layer thickness later on. So let's substitute this back. Okay, before we start solving, let's substitute this back into our energy equation. So what was it before? Before it was this thing. Okay, where did I substitute it into? Okay, here. Yeah, this is the one I want. Okay, I'll just paste it twice so that I have a template of something to change. Now you can just edit this equation bit by bit. Okay, so this was the equation originally. We wanted to substitute out this Vy. But before that, let's just make some things clear. This Vt evaluated at y is actually V evaluated at y times T evaluated at y. Okay, T evaluated at y, V evaluated at y. Alright. Just want to make that very, very clear so that there's no confusion here. Okay, so this is what it is. Alright, so now we know that we can just substitute you can substitute things out. Okay, I'm going to put a bracket in here and let's substitute Vy in wholesale. Okay, we'll substitute Vy in wholesale, and then we'll just multiply T evaluated at y into everything. Yeah, wow, it just spilled off the page again. Alright, let's see whether we can do anything about it. Yeah, I'll just move everything after the equal sign to the bottom. Okay. Ooh, alright. So, hopefully some terms start to cancel out. Okay, that is the hope, alright? So let's see whether this hope does comes true or not, or we're going to end up with a monstrosity of equations. Yeah. So let's, first thing first, I'm going to multiply this Ty in to every term. So Ty will be multiplied into this term, and this term. So there are three terms, yeah? So one is the integral term, one is the V0 term, one is the this term over here. Now again, okay, this almost spills off the page, but this is barely the max I can, the maximum I can actually take hold of. I mean, the maximum I can kind of tolerate. Okay, just to avoid confusion again, Ty is not being differentiated, so let me move it into the front. Okay, so here comes the juicy part. Or not really the juicy part, but the good part, the good news. I want you to notice this term over here and this term over here. They're exactly the same. Okay, u, t, x, and then you evaluate all of this at x and y, the big Y, and you also evaluate all of this here, u at x at y given y equals to this big Y, and then t is also evaluated at y equals to y and x equals to whatever x you want. Then you have a d by dx of this big Yx. So both these terms cancel out nicely, thankfully. Okay, so that's good news for us. Means this thing is going to be very, very much less crowded. Okay, so I'm going to cancel all of these things out, and let's see whether we can contract our equation. All right. Okay, what a relief. And then we can of course move this up. And we are almost done. Yeah, we are almost done. Okay. Okay, so now we need to put in some boundary conditions to finish it up, to tidy this up. You need to introduce some boundary conditions to tidy things up. Okay, one, no slip. Okay, one's the no slip boundary condition. Second, we will have a y, okay, this is not exactly a boundary condition, but y equals to delta t. This big Y that we want to integrate to, we want to integrate it only up to delta t, which is the thermal boundary layer. Number 3, minimal conduction at boundary layer. Or otherwise, conduction at surface is much greater than conduction at boundary layer. This is an order of magnitude analysis. So what am I saying here? You notice this del t del y evaluated at the y over here? Oh wow. There you go. You notice this okay, never mind. Let's do this one at a time, alright? Then we'll call it a day. Alright. So first let's introduce no slip. No slip means V okay, let's do itemize. Begin itemize. Alright, item, no slip. Yeah, it's always nicer in bullet point. Okay, and the last one. Ah, much better. Okay, so firstly, no slip. Okay, we introduce no slip to obtain the following. So V0, wherever you find the y velocity v evaluated as 0, all of these terms will cancel. So that's a no slip condition. No problem. Okay, that's a no slip condition. This is a partial no slip. Okay, v equals 0 at y equals 0. We haven't done it. We have not done the no slip for u yet, but yeah, the rest will be okay. Now Okay, next one is y equals to delta t, where delta t is this thermal boundary layer, which is a function of x. So let's just copy and paste this out, and let's just insert delta t wherever we find y. Okay, maybe I just put delta t, I don't put delta t, a function of x. If not, it's going to be very, very, very messy. Okay. Okay, I hope I replaced everything. So that's 1, 2, 3, and 4. I think I only pasted 3 times. There's one more time I need to paste. 1, 2, 3, 4. Oh, I pasted in all throughout. Okay. Alright, so I want you to notice something. T evaluated at the thermal boundary layer is actually T infinity. T infinity equals to T evaluated at the boundary layer. No problem. Okay, but before we can just bring this T infinity in. Okay, T infinity. Before we bring this T infinity in and assume it's independent of x, in general, T infinity equals to some function of x. Okay, T infinity is some function of x. Okay, it's not a function of y, but it's a function of x. In the special case of the flat plate flow, it is constant with x. But this is a general kind of thing. So let's make it more explicit and a little bit more generalized. Okay. And after this, you kind of know the drill. We apply product rule again. Okay, we apply the product rule again. Yeah. Apply product rule. Okay. So let's bring this T infinity as a function of x to the other side. So I'm going to copy, cut and paste it in front of the fraction. Okay. Okay, so we apply the product rule to replace this term out. Okay, we apply the product rule to replace this term out. So how, in general, what would it be like? Okay, d by dx of left angle right brace here is T infinity. This is only a function of x, not a function of y. Okay, then you have this integral of 0 to delta t u dy. Okay, what is this gonna be? We're gonna have, is this equal to, of course we have this term where we bring T infinity outside the derivative, but we also have the other term, right? You have the other term where we bring this integral outside. So we're going to bring this integral outside the derivative, and I'm going to have a bracket left, right, okay, fraction d T infinity x dx. So this is a more general case rather than the way we derived it the last time round. Okay. Now, let's make this negative t infinity blah 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 the subject. Okay, we multiply all by -1, and of course I'm going to just use t infinity instead of t infinity x, just to shorten the thing, right? So I hope it's clear to you. T infinity in general is just a function of x for boundary layer things consideration. Okay, so let's get rid of the x first, because it may take up space, makes things look a bit messy. So I'm going to -1 everything, and you might be asking, why am I doing that? Because it's going to take less steps. Okay, because why? Because this thing here is a minus, and I want to replace this whole thing. Okay, I want to replace this whole thing rather than substitute the positive t infinity del by del x of integral u dy in, and then we're gonna have some careless mistakes here and there, which I do not like. So okay, I'm gonna bring this to the other side. Plus this, and of course I'm going to reverse. I'm going to switch the left and right hand sides, which is not that important to write out, but for the sake of clarity, always for the sake of clarity, I like to write that out. Okay, so now we are ready to replace this term back in our equation. Substitute back. Okay, then we will have the following. Okay, so the good thing about this is I can just copy and paste out the minus sign as well, and then there'll be less careless mistakes. So, there's a lot of equations here. So I just substituted this part out. Okay, so this term here is getting substituted. So these two terms will replace this term because of product rule. And I'm going to bring t infinity into integral. And how do I do that? T infinity is not really a function of y, so I can just bring the t infinity in. And then I'll combine these two terms together. Okay, I'm going to combine these two terms together to again save us some space. Okay, so we will have the left hand side pretty well settled. And it looks a lot nicer, and this will be our left hand side. Very good. Okay, so what about our right hand side? Okay, on right hand side, we assume heat conduction at boundary layer negligible compared to heat conduction at surface. So what's the heat conduction at the boundary layer? It is k dt dy at the boundary layer, which is this dt dy at the boundary layer here. So what am I trying to say here? Okay, for the right hand side, okay, the right hand side is just approximately minus fraction. Okay, this is an order of magnitude thing. Okay, so we are left with this expression, and we finally get our integral solution for boundary layer. All right, excellent. Of course, if you want to take rho CP and then you just multiply it to the other side, you can, because all of the rho CP is an alpha. Alpha equals K over rho CP. Note alpha equals to K over rho CP, which is K over the volumetric heat capacity. But yeah, other than that, you see that this equation, let me copy the left hand side over, because this should be a little more compact. Than what we are getting. I copied the wrong equation over. Okay, so this becomes our integral solution, or integral boundary layer equation. All right. So we made some assumptions, this one being quite important, based on order of magnitude analysis, of course. So mostly this term is much greater than this term, so this term we can neglect. Okay, so of course if we cancel out this term, if t infinity is not a function of x, this term will disappear here. We will get back the same equation that we did before with using the control volume approach. Yeah, you'll get back this same. Of course, you divide both sides by rho CP, you'll get alpha over here. Oh, no problem. No problem at all. And of course, I made the assumption that t infinity is constant with x earlier. Otherwise, we can use the product rule here. All the same. Oops. All the same. It will be that. Okay. So yeah, it'll all be the same. You can use a product rule here, and then you will still get the same answer. But yeah, I just wanted to show you this other method, because this is a very commonly used method to get our integral equations as well. So no problem. Hope this was helpful. So the next video we might want to talk about solving this equation. So I'll stop for now, and thank you for watching. Please leave a like and subscribe if you found this useful or helpful for you. Wish you all the best.